Yeah. Okay, so this is one option. So this will print an error message for the non-existent into temp2, and then files temp1 and 1, 2 slow into temp1, right? But let's say we want to merge temp1 and temp2. And so instead of we want to write this, extend it out to temp1 and standard error also to temp1. What's the output that we're hoping for?
The two outputs will be interleaved in the file.
Yeah, the two outputs are interleaved in the file. Right? In fact, we presumably hope that F1 and F2 show up first, and then actually the non-existent files show up further with an error message saying not there. So would that work with just using close? No, you're shaking your head. It wouldn't work. Why wouldn't it work? Yeah, go back.
So you have to merge the offsets somehow.
Yeah, you got to merge the offset somewhere. I mean, if you do a close of one, you will actually close, the file stream. You do an open. What will happen is, if you do an open, you will get a new entry table, and that file script will be pointing to that new entry. And what you really wanted was actually sharing the original one. So it turns out there's one more system call that is important. You do close, create or open, you call it double. So I want to copy the file descriptor 1. And double will return the first available file descriptor. So if you did close of 2, then a double 1, then file descriptor 2 will be the same as file descriptor 1. Okay? So again, they're very carefully choosing semantics to actually make everything work out. And clearly what you see happening here, I mean, how does the design happen? Did they have this plan in their head right up front? Probably not, right? When they were using the shell, it's like, oh, this is a handy feature to have. And what do I need to change to make it happen? And so how can I change the abstraction so that actually I don't really have to write a lot of new code? All right? So we see now quite a number of system calls. We have seen fork, exit, open, close, dub, read, write. And so this gets already sort of the core, sort of the Unix system calls. Let's look at one other one that we'll spend some time talking about before I close. And that's pipes. So it's often the case, one of the things that is interesting in the Unix cells is that you can sort of want to combine multiple programs together. Right? And for example, you might want to, one way, let's say if you wanted to sort a file, you could write something like this, sort F1, and store the output in temp1, and then say you want to filter out unique words, program called unique. And read from its input and throws out all the double words that you could write in, like temp1, temp2, and let's say then you want to word count, and you want to count how many unique words were, you can write count T2. Okay? And we'll take advantage of free standard Unix programs working on that. Now this is slightly clumsy, right? Because you have to create these temporary files, and so it's much more convenient to write it in a slightly different way, which is what Unix allows you to do. You can do this. You can write, sort F1, pipe the output into unique, and the output of unique should go to word count. And that's the equivalent of actually these 3 lines of code. And these have a couple of nice particular properties. One, for example, if you have a failure in your system, you never have to clean up like the temporary files, because there are actually no temporary files at all. They're invisible, or the pipes. It's sort of an inter-process communication mechanism that hides all that stuff from you. Furthermore, it turns out that pipes actually synchronize the reader and the writer. It's sort of a bounded buffer. And so even if F1 is huge, say a little slightly smaller than the actual disk, then it would be impossible to write disk, right? Because then you need disk space more than one disk. The pipe, you can actually do the computation, right? Because this buffers 8 kilobytes of it. Okay? And then each of these programs, of course, runs more or less, if you will, in parallel. Right? if you had three processors that were sort of each running on their own processor and sort of handing data from one to the other through the pipe. Okay? So this is a very convenient mechanism that a lot of that the shell provides, and that is a good way of combining little programs together and writing more complex programs. And so many people use the shell, and I presume many of you do that too, is like you use the shell actually to write basically programs. Shell is a scripting language, and you can write amazing programs in the shell. In fact, in a full functional shell, you can basically write a compiler or a new shell or whatever you want. It's just a full, complete programming language. It doesn't have all the abstractions that you might want, but in principle it has. Okay? So, anybody know how pipes work? Yeah, you're back. Too much Unix programming there.
You match up the standard input and output between processes so that they talk to each other as if they're piped directly into each other.
Yeah, I mean, you can sort of see this. What you want to happen here, correct, is that sort F1 is going to print to file descriptor 1, correct? And what we want to arrange is basically that file descriptor 0, correct, reads from the output of file descriptor, from this file descriptor once. So we want to set a pipe that basically connects file descriptor 1 of this guy to file descriptor 0 of this guy. And that's going to be our goal. So to do that, Unix introduces one more system call that we care a little bit about. So there's going to be pipe actually returns two file descriptors. The pipe system call is engine file descriptor. Basically, there's a system called pipe. And we pass it in FD, and that will fill in two file descriptors in this array of array of integers. And the first file descriptor in this array is the input, the reading side, and the other one is the writing side. And so the reading side is like FD0, like similar to the 0 input, as if I can remember, and FD1 is going to be the output similar to 1 as a standard output. Okay? And basically what it is, it's a one-way communication channel. You write something into 1 and you read it out of 0. And you can have the same process read it out of it, it's going to be slightly messy. So it turns out this is sufficient, this one extension is sufficient to actually implement pipes. And Unix shell commands like this. And so you can see how it works. If you look at sheet 77. On the right side, you can see there's a statement case pipe. And that's the implementation of the pipe symbol. And you see actually what happens here. You call fork, and so this you can imagine that is sort, right, being created. And what does it do? It's going to close file descriptor 1, correct? Because we don't want to use the standard output. We want to do something else. It's going to dump P1. P1 was the output file descriptor, correct? And so that will be now file descriptor 1, because that's the first available file descriptor, and it will point to the same file descriptor as FD1 points to. Right? So somewhere in memory, there's a table of file descriptors or buffers, and they're now lining up correctly. Right? And the close is P0, because that process doesn't need it at all. It's not going to read from that side of the pipe. And then the close is P1, because it wanted to enforce the rule that only 3 file descriptors are open when we fork up when we exec the new process, right? And then we exec unique. And now unique starts with 3 file descriptors open, 0, 1, and 2, and 1 happens to point to the input of the pipe, right? And so in the other process, we close 0, right? Because we're going to read from that side of the pipe. We're going to dub P0, and the file descriptor 0, the 0 entry in the file descriptor array that the pipe created. And then close P0 and close the rest of the pipes, right? And then run basically unique. And so this sets up exactly with some small file descriptor manipulation. Shell sets up this pipeline. Okay? Make sense? And you will be implementing pipes in your shell at the end of the semester too. And again, you will be very proud. You might get this wrong in the first try, but in the end, hopefully, you'll be very proud when you can actually type in something like this and get that full generality of having programs work together to make larger programs. Okay? So hopefully I convince you that looking at this Unix abstraction in a bit of detail is interesting, because you can see that they're very carefully designed so that you can implement a shell, a very powerful user interface with very few mechanisms. And because the mechanism that we're only using here is fork and exit, and basically this file descriptor table, and some rules about what happens on an exec and a fork, which file descriptors do you inherit and what do they mean. Okay? So what we're going to do the rest of the semester is basically implementing these abstractions. Right? We're going to implement fork, exec, the file descriptors, file system, and we're going to be basically studying how you do that. And so it turns out that implementing fork and exec actually there's a whole bunch of mechanisms. We haven't really talked about it. I basically said, well, there's a proc table. Right? Well, it turns out there's a bit more to it than just a proc table. All right? So on Monday we'll talk about how the first process comes to existence. So the birth of Unix, basically, if you will. Okay? I'll see you Monday. And lab 1 is posted, so you can go up.